Hello and welcome to Precalculus lesson number 33. In this video, we're going to learn about systems of linear and nonlinear inequalities. We'll start with some linear inequalities. When we're dealing with these types of inequalities, the best method to use is the one that helps us understand what's going on, and that would be to go ahead and put each of these inequalities into slope-intercept form. And of course, as you can see, they're all very much related. So if we put one into slope-intercept one form, we've pretty much handled the others as well. So let's go ahead and look at that first inequality, part A. So we're going to go ahead and solve the inequality for y. So that means we're going to go ahead and move the negative 4x to the other side, where it becomes positive 4x plus 12, right? So now we're going to go ahead and divide both sides by 3 to get y by itself. So we get y is greater than or equal to 4/3 x plus 4. Now, the first thing we want to do when graphing an inequality of this type is go ahead and graph what we call the boundary line, which is basically is going to look very much like that, except with an equal sign. So the boundary graph will be the graph of y equals 4/3 x plus 4. All right, so the y-intercept is obviously 0, 4, right? That's the y coordinate of the y-intercept, and the slope is 4/3, right? Which you can think of as positive 4 over positive 3, but you can also think of it as negative 4 over negative 3. That means if you have a point on this graph, such as the y-intercept which we possess, 0, 4, to get to another point, you can go up 4 and 3 over to the right, or you can go down 4. Remember, the top of the slope formula is the change in y. So you may go down 4 and then left 3. Now, because of the screen that we're looking at, it'll be easier if we look at that. So from here, we go down 4 and left 3 to get to another point. And then we draw the line, okay? Now, if it says greater than or equal to, that means points on the line itself are going to be part of the solution set. And greater than implies all the points whose y value, all the points in the plane whose y value is greater than the y values on this line, right? So that would be what? That would be all the points above the line, right? So when you see greater than or equal to, once you're in slope-intercept form, remember, you're going to want to graph points on or above. So that means we're going to shade this part as well, okay? Now, the next one looks very similar to this one, except it's strictly greater than, right? So we don't need to go through all these steps anymore. We've already done it. So we're just going to write it as y greater than 4/3 x plus 4, right? Because we want the points in the plane whose y value is strictly greater than the y value of the points on this line. That means the points on this line themselves are not going to be part of the solution set, because that's where y is exactly equal to 4/3 x plus 4. So we're only going to want the points with y values greater than the y values on this line. So therefore, that would be all the points above. So when you see greater than, just remember that's going to indicate above. above the what? The boundary graph. All right, so we would only shade that part, okay? Now for this one, again, pretty much everything is going to work out the same, except we're going to have y less than or equal to 4/3 x plus 4. Now, of course, because these are inequalities, we are very careful that if we divide by a negative, we'll make sure we switch the direction and all that. So, but in this case, it's positive. We don't need to really worry about that. So when you see that, that means you're going to be interested in the points in the plane that are because of the equal on and because of the less than or below the boundary graph. So we already have the solid line here. So we're going to just shade the part below as well. All right, so that would be the graph of the solution set of this inequality. For the last one, we're going to have y less than 4/3 x plus 4. And when we see that, we're only going to be interested in points that in the plane that are below the boundary graph. Just like that. So you want to make sure that you don't go above at all. Okay, so you have to kind of do this delicately. Of course, on computing systems, you just click the paint tool and it shades it for you. But being able to do all this stuff by hand is priceless, because that's where you really gain your understanding of what's going on. Okay, that's how you handle these linear inequalities. Let's go ahead and move on. All right, as you know, the boundary graph here is going to be, this is very simple. So the boundary graph is just going to be the graph of x equals to, right? And that, as we know, is just in the plane is a vertical line going through x equals 2. If you're on the number line, right? If you're on the number line, x equals 2 just looks like a point at 2, right? But when you're on the plane, you want all the points whose x value is 2. So, and of course, think about it. For every point on this line, what's the x value? For example, this is the point on the axis is the point 2, 0. This one is the point 2, 1, right? This one is the point 2, 3, etc., right? Down here we have, for example, 2, -3. What do they all have in common? Their x value is 2. So when you graph all the points in the plane whose x value is 2, you actually end up with a whole line, right? So now, let me get rid of these real quickly, now that you understand them. All right, so with these vertical lines, this is the only time you really can't talk about above or below, right? So here we're looking for points in the plane whose x value is going to be greater than 2. So think about it. That's going to mean what? To the right of, right? So when you're looking at x greater than or equal to 2, you're going to look at points on or to the right of the boundary graph. Okay, so you would shade to the right of the boundary graph as well, right? All right, so this one, the next one, wants only the points in the plane whose x value is strictly greater than 2. So you're going to shade only the point on the right of the boundary graph, and you're going to dash the boundary graph because it's not going to be included. So you're only going to have this part shaded, right? All right. For the next one, less than or equal to 2, right? So we know the boundary graph is x equals 2 as depicted here. So this means you're going to want, so remember the last one was you're going to want the points only to the right of. For this one, x less than or equal to 2, you're going to want all the points on or to the left of, because that's where the x values are. For every point in this region, right, that I'm showing, the x value of that point would be what? Less than 2, right? And for every point on the line itself, the x value is 2. So you want all the x points whose x value is either 2 or less than 2. So it'll be the line or everything to the left. So that's why we say either on the line or to the left of the boundary graph. All right, so just shade this part. All right, and for x less than 2, then you're not going to want the points whose x value is 2, so that's why this graph is dashed, right? Meaning this line is not included, but we still need it so that we can shade to the left of it. So we only want the points to the left of the boundary graph. Now, sometimes it's just called boundary line. I'm using boundary graph because we're not only going to be dealing with linear scenarios in this section or in this video. So we need to make sure we're ready once we get to the curved graphs as well. All right, so that's how you do those. Go ahead and do this one on your own, see what you come up with, and then see if we agree. All right, so it's very similar to the previous one, except that in the sense that it's a special case. But here, these are the kinds of lines. Horizontal lines are lines that you can talk about above or below. So the only ones we can't say above or below are the vertical ones, right? So here, this is going to be what? You're going to be interested in the points that are, here's the boundary graph, right? Y equals 2, so that means the horizontal line going through y equals 2, and you're going to want every point on or above the boundary graph, which is y equals 2. So basically you're going to want to shade above. For this one, you're going to want strictly the points that are above, right? So that's why the boundary graph itself is dotted or dashed, and we're only going to shade above it. All right. For this one, we're going to want all the points that are in the plane whose y value is basically less than or equal to 2. So the points that are on or below the boundary graph. Okay? And for this one, we only want the points whose y value is strictly less than 2. So we don't want the points on the line, that's dashed. So we want only the points below the boundary graph. Just like that. Okay, so these are the special cases. All right, here's one involving parabolas. As long as you're dealing with functions, it's possible to just get y on one side and then everything else on the other side, right? So we know how to graph a parabola like this very easily, right? You just know that in this case, the vertex is going to be 1, 4, right? Because the general form is y equals a times x minus h squared plus k. In this case, in which case the vertex is at hk. So hk here is 1, 4, right? So notice that we start at the vertex, then we can go 1 point to the left and 1 point to the right of it to get a couple of extra points. We plot those and we can get a really good graph of our parabola just like that, okay? So now we want all the points in the plane whose y value are greater than or equal to the y value on this parabola. So basically the parabola itself is going to be part of the solution set. That's because that's where the y values are exactly equal to x minus 1 squared plus 4. And we'll go ahead and take everything above. So we're going to shade above this parabola. Okay? Now, many sites and textbooks teach you to try test points, and that's fine too, because basically if you pick a test point in here, you'll see that it's going to satisfy this inequality, and if you take one here, you'll see that it will not satisfy. So you have to pick a point for your test point that is definitely either below or above, right, the parabola, and you can do it that way. Let's say, for example, we take this point right here, 1, 3, right? Notice that if I were to, this would be the test point approach. So the test point 1, 3, if I plug it in, right, what do I get? I get 3 is greater than or equal to test point, the x value is 1, so 1 quantity 1 minus 1 squared plus 4, right? So I get 3 is greater than or equal to 4. Now that's false, right? That means this test point was in a region that is not the solution region. So what's the other region? Up there. So you know that that's where the solution region is going to be. Okay, test point approach is fine. I mean, I have nothing against it. It's just that I think doing it using the understanding of where the boundary curve is and whether you should be above or below it is much more intuitive and understanding based. All right, so as you can imagine, for the next one, right, we're only going to be interested in the points that are above the parabola, not on, right? So because of the strict inequality. So that's why we have the parabola itself dashed. We're going to, this is of course right here is our boundary graph, this function that we've graphed here. So we want all the points above the boundary graph, okay? So we just basically just shade above, okay? For this one, less than or equal to, we're going to want all the points on or below. Whenever there's an equal to, that means the boundary graph itself is part of the solution. And then you have to decide whether you need to go above or below. So on or below the boundary graph. So here we're going to shade below. All right. For the next one, of course, we're only going to want points whose y coordinate is going to be less than the boundary, that of the boundary graph, so we're only going to shade below. The boundary graph itself is graphed dotted. Okay? And that's how you do that. Do note that so far we're just getting warmed up with just inequalities themselves, right? we haven't really done a system yet. These are separate problems. You understand that, right? This is not one system of inequalities. These are each independent problems of their own. I'm just representing them on the same screen because they're so closely related, right? Otherwise, they're completely separate problems. We haven't done any systems yet. All right, so here we have y greater than or equal to 2 to the x plus 3. So y, which is f of x, is going to be 2 to the x plus 3. Here we plot a few points. We graph. Now for this one, it's greater than or equal to, so this is our boundary graph. You know that we're going to be on or above, right? For the next one, right, the boundary graph itself is not going to be included because we want points that are strictly above, right? Greater than. So the y values should be strictly larger than the y values on this boundary graph. For the next one, we're going to be on or below, right? So the graph is solid, and we also shade below it. So the boundary graph as well as every point below it are going to be the solution set. For this one, we're going to only want points that are below, right? All right, why don't we try a test point for, say, this one. All right, so let's take the point 0, 2, right? Or let's do one that actually turns out true this time. Let's take 0, 6, okay? So if we've shaded the correct area, then this point 0, 6, this test point, should make this inequality true. Let's see if it does. So y is 6. We want to know if it's greater than 2 to the power of 0 plus 3, right? Notice the x is 0. So we want to know if 6 is greater than 1 plus 3. We want to know if 6 is greater than 4. Well, that's true, right? So I can get rid of the question mark because I'm not checking anymore. I verified it. So now I know that's true. So that it means that point 0.06 is on the side of this graph which is shaded. So we've shaded the correct area. So that's the test point approach. And the intuitive geometric approach is, of course, with the above or below and all that. Okay, so that's how you do that one. All right, here, as you know, we are looking at boundary graphs that are circles, because the boundary graph will just be x, quantity x minus 3 squared plus quantity y minus 4 squared equals 9, right? So we know that this is a circle with center at 3, 4, and radius 3, right? So there it is. Center at 3, 4, and radius is 1, 2, 3, right, on all directions. Now, because it's not very easy or convenient to express a function out of a circle, in fact, it's impossible. The circle itself does not represent a function. As you see, it fails the vertical line test. However, as we have discussed before, you can turn it into a function describing the top and one describing the bottom. So it turns into two functions. Anyway, that would not be the easiest approach to try to rewrite this as a function, even though it is possible, but remember, as two functions. So the test point approach is actually better for these particular types of graphs. So here's a perfect test point, 3, 4, the center, okay? So see how the center fares, okay? If it satisfies the inequality or not. If it does, then it's going to be part of the solution graph, and if it doesn't, it's not going to be. It's going to be the outside of the circle area that's going to be the solution. So just plug in 3, 4. Why is that ideal? Because it's so quick, right? So if you do test point equals 3, 4, Notice that's obviously going to make the left side 0 because 3 is going to make this 0, 4 is going to make that particular expression 0. So we get 0 plus 0. We want to know if that's greater than or equal to 9. And of course, 0 is greater than or equal to 9 is false, right? So that means the solution region is not inside the circle, but rather what? Outside the circle. Okay, we get the sun graph, right? All right, so notice that this is actually the way it kind of turns out. It's really nice. So if we're looking at greater than or equal to, you're going to be outside. If you're looking at less than or equal to, you're going to be inside, okay? As you can see, if this were less than or equal to, right, as is here, it would have become true, right? So in other words, if we use the same test point here, we would have had 0 plus 0, which is 0. Is that less than or equal to 9? Yes, that's true, right? We don't need the question mark, right, at that point because it's true and it's verified. So for this one, you would shade on the circle or inside the circle, right? Now, where would this one be, do you think? Only outside the circle, right? That's why the circle itself is represented in dashed format because it's not part of the graph, right? And for this one, the last one, as you would imagine, only the inside of the circle. Okay? And that's how you do those circular ones. All right, so here's our first system of inequalities. Now, the thing that we need to do is to make sure that we satisfy both of those inequalities. So for the first one, if I put this in slope-intercept form, I get y is greater than or equal to negative x, right? For the second one, I get negative y is greater than or equal to negative x plus 3, which implies now we're going to multiply both sides by negative 1, which means we immediately have to change direction of the inequality, the direction of the inequality. So we get x minus 3, y less than or equal to x minus 3. This one is already done. I'm just going to rewrite it so we have our system together. All right, so basically, let me write them here. We have y greater than or equal to negative x, y less than or equal to x minus 3. So the boundary graph for the first one is the line y equals negative x, right? As you know, that's this line right here in the blue. It's very easy to graph, right? Just do a couple of points or just use the slope-intercept. So the y-intercept is 0, 0, and the slope is negative 1. So start there, go down 1, right 1. There you go. There's the graph of the y equals negative x. And for this one, the boundary graph has equation y equals x minus 3. So the y-intercept is 0, negative 3, and the slope is 1. So you're going to go up 1, right 1, and you get the red graph, right? Now, remember, you're going to want y is greater than or equal to x. So for the first one, you want the points in the plane that are on or above the boundary graph. For the second one, you're going to want the points that are on or below this boundary graph. So since we have these in different colors, we could use those names, or better yet, let's just give them names. So here's L1. Let's call the first one L1, the first boundary graph. Let's call this L1, and let's call this L2. So we're looking for points on or above L1, and remember, simultaneously on or below L2. So here's L1. So we want to be on or above the blue line, but on or below the red line, right? So what region, if I were to give these regions names, right? Let's say this is region 1, 2, 3, 4, right? So which of those 4 regions would satisfy both of those conditions? So that it's on or above L1, but at the same time on or below L2, which is the red graph, right? As you can see, I didn't name it 1 on purpose. It just worked out that way. So the solution graph would indeed be region 1, right? Think about it for a second. See? This region is on or above the blue line, but at the same time it's on or below the red line, right? So that would be the solution region for that one. Okay? All right, so make sure you're comfortable with that and we'll proceed. All right, so the next one is a nonlinear system. The first equation, as we know, the first inequality has a boundary graph associated to it, which is a circle, right? So that circle has a center at 0, 0, of course, because you can write it as quantity x minus 0 squared plus quantity y minus 0 squared equals 3 squared, right? And the radius is 3. So because it's less than, we know that we're going to want the points that are inside, right? So we want the points that are inside the circle, not on the circle, because it's strictly less than, right? And for the line, this is a linear one. Let's go ahead and look at that one. So we're going to go ahead and solve it, put it in slope-intercept form. So we have 5y less than or equal to negative 3x plus 15. Divide both sides by 5, so we get y less than or equal to negative 3/5 x plus 3. And the boundary graph is the equation y equals negative 3/5 x plus 3. All right, so let's call this boundary graph 1. And we call this one the 2, since it was the second one we graphed. So we call this BG2. We don't need the dots, do we? And we'll call this one BG1, right? All right, so because of the less than or equal to, we know that means on or below the line, right? So we want the points that are strictly inside BG1. So this is what we want. Points inside BG1 and on or below BG2. All right, so remember, this is what we're calling, the line is what we're calling BG2. The circle is what we're calling BG1, right? So we want points that are inside, right, the circle, but they also have to be below, on or below the line, right? So that means we're just going to not want to include this part, but everything else inside the circle, right? Because that little part is above the line, right? So we don't want that. There it is. Is that nice and easy? It is, right? Okay, so that's how you handle those. For this next one, we have 4 linear inequalities. You encounter these quite a bit if you ever end up taking linear algebra and do what's called linear programming. All right, so these are all very, very easy to deal with, right? So we're only going to take this one and put it in slope-intercept form. So we have 2x plus 4y is less than or equal to 4, so 2y. Make sure you keep the inequality sign until you've gone to slope-intercept form, because we need to know whether there's going to be a change in direction and all that. So make sure you don't just turn it into an equality right away, okay? So 4y is less than or equal to negative 2x plus 4. So y is less than or equal to, now we're going to divide both sides by 4, right? So we get negative 1/2 x plus 1, correct? So the boundary graph associated with it will have equation y equals negative 1/2 x plus 1. We'll call that B1 since there's 4 of them. For this inequality, the boundary graph equation will be x equals 6. We'll call that B2. For the next one, the boundary graph equation will be x equals 0. We'll go ahead and call that B3. And for the last one, it'll be y equals 0. So we'll call that B4. All right, so notice that because of the less than or equal to here, we're going to want the points in the plane that are on or below B1. And remember, we got to satisfy all 4 inequalities. For the next one, we're going to want the points. Remember, this one is a vertical line, so we don't say on or below or all that. We say to the left of, right? So we want points strictly to the left of, because it doesn't say less than or equal to. So to the left of B2. For B3, we're going to be on or to the right of. So, and on or to the right of B3, which is this vertical line, which is the y-axis itself. And for the last one, which is y equals 0, which is the x-axis itself, which we call B4, we're going to want to be below. So, and below B4. So remember, we need to satisfy all of these conditions. So on or below B1. So that means here's, let's go ahead and label these. So the red one is B1, right? B2 is the line x equals 6. B3 is the x-axis, right? I mean the y-axis, sorry. The line x equals 0. And B4 is the x-axis, the line y equals 0. All right, so we want to be on or below B1. Okay, so here's the red one, B1, on or below. So that means what? Don't look up here at all anymore, because no point in that region is going to be in the solution set, because otherwise it would not satisfy the first inequality. And remember, we have to satisfy all inequalities. So now only look on or below the red line as we move on to the next one. We also want to be to the left of B2. So That means don't look to the right here anymore either, right? And on or to the right of B3. So we're going to be on or to the right of B3. And we also want to be below B4, right? So we have to be below the x-axis as well, right? So I think if you think about it carefully, you will notice that the only region satisfying all of those requirements will be here. Let's go ahead and graph it, and we'll check it real quickly. Is it on or below B1? Yes, it is. Is it to the left of B2? Yes, it is. Is it on or to the right of B3? Yes, it is. And is it below B4, which is the x-axis itself? Yes. So remember, the solution region is everything I've shaded, also this little piece of this line, and also this part of the y-axis, okay? Which of course, this part will go on ad infinitum, right? Forever. Okay, so that's how you would handle a system of inequalities like that. Make sure that that makes sense to you, and then we'll proceed. All right, here we have another nonlinear system of inequalities. So the boundary line for the first inequality will be B1, which is represented by the equation y equals log x, and the second boundary line will be represented by y equals absolute x minus 6. Now, we should know how to graph these by now, right? Remember, for example, for the first one, we have y equals log x. Remember, that means log base 10 of x. So if we put it in its exponential equivalent form, we get x equals 10 to the y, right? So now if we just make a quick table. Now, don't forget that here we're going to give y values and then find the corresponding x values. So let's say I just do -1, 0, 1, right? So -1 gives me x equals 10 to the -1, which is 1/10. 0 gives me 10 to the 0, which is 1. And 1 gives me 10 to the 1, which is 10. So since we know the basic shape of the logarithmic graph, those should suffice for us to get a pretty decent graph, right? And for this one, remember, for those, that's just the graph of absolute value of x, which we know is the famous V shape, shifted 6 units to the right, right? Translated 6 units to the right. All right, so where are we going to look? We want to be, because of the less than or equal to here, we want to be on or below B1, and because of the greater than or equal to, we're going to want to be on or above B2. Remember, we're calling the blue graph B1, the blue function there, and the red one is what we're calling B2, right? So we want to be below the blue curve here, right? The log curve. So don't look up here anymore. And at the same time, above the red one. So we can see where the solution set is, right? It's that little, it's kind of triangular shape there. Of course, you know it's not a triangle because that part there is not a straight line segment. So don't mistake it for a triangle. All right, that should pretty much cover it for this lecture. Just remember, if it's possible to get y on one side and everything else on the other side, which is for functions, it's ideal to do that and then to consider whether you should be on, above, below, etc. And if it's not, such as in the case of a circle, then just go ahead and use the test point method that we outlined earlier, okay? And that should do it. Take care until our next meeting.